Permutation, where some objects are repeated. Consider the number of permutations of the letters G, E, F, E, A, T, E, D. There are 3 E's and 2 D's. 1, 2, 3 E's, 1 and 2 D's. The number of permutations of D1, E1, F, E2, A, T, E3, D2 is 8 factorial. But E1 and E2, E3 can be arranged in 3 factorial ways. And D1, D2 can be arranged in 2 factorial ways. So, the number of arrangement of D1, E1, F, E2, A, T, E3, D2 is 3 factorial times 2 factorial times the number of arrangement of defeated. Okay? And therefore, the number of permutation of defeated is 8 factorial over 3 factorial times 2 factorial equals 3,360 ways. Generalizing this argument, we see that the number of permutation of n objects comprising of R1 identical objects, R2 identical objects, until Rk identical objects is n factorial over R1 factorial times R2 factorial times until Rk factorial. Example 15. How many different permutations can be made using the letters of words? 1. Books. 2. Lotto. 3. Mathematics. Solution. For books, we have altogether the number of objects is n equals 5. Then R2, the identical objects here is 2 for O, O. So therefore, the number of arrangement of the books is n factorial, over R factorial equals 5 factorial over 2 factorial. Okay, and then you can use the calculator. Okay, so you have 60 ways. For Lotto, we have the number of objects here is 5. And we have identical objects of O, O is R1 equals 2, and TT, the other identical objects, we have 2. So therefore, the number of arranging this word, Lotto, is n factorial over R1 factorial times R2 factorial, the repeating of identical objects. So 5 factorial over 2 factorial times 2 factorial. So you have here 5 times 4 times 3 over 2, and you have 30 ways. For mathematics, the number of objects involved in mathematics is 11. And we have the identical of repeating objects. For R1 is for M we have twice, so equals 2. And we have A also happened twice, so R2 equals 2. And the other one is T, okay, also happened 2 times, so R3 equals 2. So therefore, the number of arranging this mathematics, okay, is n factorial over R1 factorial times R2 factorial times R3 factorials equals 11 factorial over 2 factorial times 2 factorial times 2 factorial. And this is equals 4989600. Example 16. There are 2 copies, each of 3 different books, to be arranged on a shelf. In how many distinguishable ways can this be done? Solution. How many books involved? Okay, that is n equals 2 times 3 equals 6. There are 6 books. And each book, we have 2 copies. So if R1 is 2, R2 equals 2, and R3 is equal to 2. So the number of ways to arrange the 6 books is n factorial over R1 factorial times R2 factorial times R3 factorials equals 6 factorial over 2 factorials times R2 factorials times 2 factorials. Okay, you can calculate this using your calculator. We have 90 ways. So there are 90 ways to arrange 2 copies of each of 3 different books on a shelf. Example 17. How many different 10-letter codes can be made using 3 A's, 4 B's, and 3 C's? Solution. Altogether, we have n equals 10. Okay. Now R1 is 3 times 4, 3 A's. Now R2 we have 4. Okay, so R2 equals 4 here, 4 B's, and 3 C's. So R3 is 3. So the number of ways of 10-letter codes is 10 factorial over 3 factorial times 4 factorial times 3 factorial. And then we have the number of such code is 4,200 ways. Example 18. In how many ways can 3 red, 4 blue, and 2 green pens be distributed among 9 students seated in a row if each student receives 1 pen? Solution. The number of permutation is 9 factorial over 3 factorial times 4 factorial times 2 factorial equals 1,260 ways. So for the 3 red pens is considered as repeating of identical objects. So for these 4 blue pens and 2 green pens. Example 19. In how many possible permutations of the letters of the word adding are the 2 D's together? Secondly, we have are the 2 D's separated? Solution. There are 5 different items. We have A, okay, D, okay, D, and D. They are identical objects. I and a G. So we have 1, 2, 3, 4, 5. Okay, so we have 5 factorial ways. So the number of possible permutation is 5 factorial. So we have 120. The number of arrangement with D separated is by finding first the number of arrangement without a restriction and minus the number of arrangement with D's together. So now the number of arrangement without restriction is 6 because adding ADDING we have 6 objects, and we do have this repeating of identical objects of D. It happened twice, so 2 factorial. So we calculate this. We have here 6 factorial over 2 factorial. Okay, and then the number of arrangement of these are separated. We just go to have, okay, this is without restriction, 6 factorial over 2 factorial, and then we minus D, okay. D is together. So minus 120 or 5 factorial. Okay, the values of the 6 factorial over 2 factorial is 6 times 5 times 4 times 2. Okay, and then minus 120 we have 240. Example 20. How many different arrangements are there for the letters of the word arrangements if A begin with R and ends with E? B, the two letters E are separated. C, the two letters E and the two letters A are together. D, the consonant letters G, M, T, S are together. And E, the two letters N occupy both ends. Okay, if you go to this arrangement, the word arrangement, we have A happen twice, R happen twice, N happen twice, G once, E twice, M once, T once, and S once. And then we start with A first, begin with R and ends with E. So it can be picturized using this box. Okay, we have R, beginning with R and ends with E. Okay, all together we have 12 alphabets. So the left behind one is 10 letters. So the number of permutation is we go to arrange these 10 letters. Okay, which is 10 factorial over 2 factorial over 2 factorial. Because now this is 2 factorial and 2 factorial is coming from A, okay, and another 2 factorial for N. So we'll have here 97,200. Okay, and this one when it is fixed, when R, okay, begin and end with E is already fixed, so we have 1 times 1. Okay, that's how to altogether now we will have only to arrange 10 letters. Okay, so we have 907,200 ways. Okay, now we go to B. The number of permutation of two letters E are separated. So it is also equal without restriction, minus E together. Okay, if it is without restriction, we will have altogether is 12. And we have twice here for A, so 2 factorial. R, we have 2, so 2 factorial. And we have 2 factorial, and E, we have 2 factorial. This is without restriction, okay? And then minus E together, okay? When we minus E together, this E must be together with block E. Then the left behind one, the alphabets, is 10 letters, okay? 10 letters. And then this E is considered as, okay, the E together is considered as one object, okay, and the balance is 10 objects. So altogether we have 11 objects. But we still have some repeating objects inside these 10 letters, okay, and then we have 12 factorial over 2 factorial times 2 factorial times 2 factorial times 2 factorial, and then minus, okay, just as I said just now we have 11 letters, so 11 factorial, and we have 2 factorial over 2 factorial times 2 factorial times 2 factorial. Where this come from? This has come from for A, 2 factorial for A, 2 factorial for R, and 2 factorial for N. For E is already taken here. Okay? And then total is 24948,000 ways. Okay, now we go to C. The two letters E and the two letters A are together. Okay, now we try to group E, and AA. Okay, we'll group E, and AA. So we have like this, and what are those alphabet that not blocked yet? So 8 letters. This is still not blocked yet because you want this E and A are together. So but we have this 8, inside these 8 letters, we still have repeating of identical objects. There's 2R and 2N. So how many objects that we have to arrange? The number of permutation is, this will be 8 objects. This considered as 1 and this considered as 1. So 1, 2 plus 8 is 10 factorial. Over 2 factorial times 2 factorial stand for this 2R and so 2N inside this 8. Okay, 8 factorial. So times 1 times 1. And times 1 coming from here, E, because this E and also this E, we consider it as 1 because this E and this E, they are not different or they are not distinct, but they're all the same thing. This is repeating of identical object. So we consider this as 1. And so for this, A. So therefore, we have to times 1 times 1. Okay? And then the number of ways is 907,200 ways. Okay, now we move on to D. The consonant letters G, M, T, S are together. So this G, M, T, S, the alphabet, they must be together and we block them. Okay, to be just one object. Then plus. Okay, the remaining objects is 8 because 4 plus 8 is 12. Altogether just now is 12 letters. Okay. Okay, so the red one is already taken as 1. We put or we block it. We block this GMTS. And the number of permutation that we are going to arrange is 9. This is considered as 1. Okay, and then we have 8 letters. Okay, and then within these 8 letters, we have the black one. E, we have 2 twice. Okay, so 2 factorial. And we have 2. Okay, so 2 factorial. So for the R and so A, 2 factorial, 2 factorial. Times, okay, 4. This 4 is coming from GMTS. Okay, because GMTS, they are distinct or they are different objects. We still have to arrange them, okay, which is denoted by this 4 factorial. And the number of ways is 544,320 ways. And E, the 2 letters N, occupied both ends. Okay, so if you try to picture this out, it can be like this. Okay, both ends is occupied by N, so this will N, the N. Okay, what are those alphabet that still have got to be arranged? Okay, that is in the middle one. Okay, in the middle of this N, also N. Okay, inside here, it should be how many? 10 letters. Because 2 and 2 is already taken. Okay, so the one that we have to arrange is 10 letters. Okay, the number of permutation is 10. Okay, factorial over 2 factorial times 2 factorial times 2 factorial times, okay, 1 is from here. It is already fixed here, also 1 way, and the last one also 1 way for this times 1. So you have 4 5 3 600 ways.